Hello everyone. In this video I'd like to demonstrate how we can do some basic linear algebra operations using Python. So I'm in a Mac OS terminal here and I'm going to go to the Python interactive interpreter called IPython. And here we have it. Now the first thing we want to take a look at is list. To create a list in Python, you simply enclose the entries using brackets and you separate the entries using commas. So here I have created a list called A. And let me create a second list and call that one B. So if we use this type command to see what type of object A is, it returns that A is indeed a list. Now, however, if we try to do some math operations on it, we get these unexpected results. Like 2 times A is basically taking the list and repeating it 2 times. And notice what we get if we do A plus B. Okay, instead of adding the entries, it just concatenates those 2 lists. So clearly we can't use list to represent our vectors that we use in linear algebra. And what we're going to have to use are Numpy arrays. And Numpy stands for numeric Python. And before we could use Numpy, it's a module that has to be imported. So we'll use the command import Numpy as the standards. We like to abbreviate it NP. So if we're going to do some operations from the NumPy module, we would have to start with an NP. So hey, let's create a NumPy array now. First of all, I want to delete those 2 lists that we had. And I'll create a NumPy array using this syntax here. The array is 1, 2, 3. And there we have created a one-dimensional NumPy array. Notice what we get if we check out what the type of object that is. It is a n-dimensional array, NumPy. And here, if we take 2 and multiply it by A, we get the expected results. Let's create another array. B is equal to np.array 4, 5, 6. And we can take A and add to B and get the sum of those 2 arrays. Now to see what size this array is, we have this, for example, what size A is, we take A, we hit dot, and this is a method for this NumPy object called shape. So I hit a.shape. We see we get this peculiar looking thing here, 3 comma blank. So what that's telling us is that it's not a vector, and that it's not like a 3 by 1 or 1 by 3. It's just an array with 3 entries. And so to create a vector, for example, if you want a column vector, you would do the following. You could say A is equal to A dot reshape, and let's make it 3 by 1. Now notice when we type A, what it looks like now. It's a 3 by 1 column vector. And if we do A dot shape, we'll see that it's 3 by 1. Now B, let me delete the B that we have. Let's create a second vector. B is equal to np.array. One way you could create a vector is this. 4, 5, 6 dot reshape. So there B is a column vector as well. And we can do a scalar multiplication on these. For example, I could take 2 times B and there's a result. If we want to assign that result to another vector, let's say C, the vector C is equal to 2 times B. So here we have C. Now, these vectors, if you try to take, so A and B are both column vectors. If I take A times B, what that's going to do is, let's see what A and B look like again. Usually we don't define multiplying two column vectors together, but what Python will do is just multiply the entries. See, it's 1 times 4 where you get the 4, 2 times 5, and sometimes that's a useful operation. It actually has a name. It's called the Hadamard product. But to multiply vectors or matrices in Python, the command or the operator that you use is this ampersand. So this is used for matrix multiplication. So let me try to multiply A times B. And think for a moment what you think we're going to get. We have two column vectors, and we're going to do a matrix multiplication. Well, we're going to get an error because those two shapes do not align. The number of columns in A has to be correspond to the number of rows in B. Now, what is defined is I can take the transpose of A. So the transpose operation will take a column vector and turn it into a row vector, or vice versa. So let's look at the way you take a transpose is do A dot uppercase T, and notice it turned A into a row vector. It just returned that. It didn't change A. So what we can do, now hey, notice what you get here, A dot transpose dot transpose. Well, you're taking one step forward, one step back. You're going to be back to where you begin. All right? So I want to have A transpose matrix multiply that times B. Now that's going to be defined, and that is the dot product of A and B, which is 32. Let's see if that's right. A, B. Yep, that'd be 32. Now, you can do the dot product this way as well. Numpy dot v dot vector dot A comma B, and we get the same result, the dot product. So we have to be careful. Are you working with just a basic array, or are you working with a column vector or a row vector? Okay. So if I take A, transpose it, which gives me a row vector, and try to multiply that by B transpose, I'm now taking two row vectors. They're not going to align, and we're going to get an error when we return. Now, so far what we can do is we have some variables defined, and we can type who into the command, and it will show us what our current variables are. We have A, B, C, and we have this module MP, Numpy loaded. If we hit who's this, it'll tell you a little bit more information. We have A, an array, B an array, C an array, and we have this module. And here notice it tells us some information about the variables. So this is something nice about IPython. Also, we had just used this command mp dot, and perhaps you don't remember exactly what that command was. You knew it started with a D, and what you could do is you could type np, put a asterisk question mark, and it will show you all of the operations that start with D here. Return that. Okay, so you have difference, etc. Okay, so see how we did that? We did np.d question mark. If I want some information on this dot product operation, I can put a question mark after it, and it tells you about what it does. It explains the dot product. It gives you some examples. Again, this is in IPython. Well, we're going to go and look at a matrix. But before we look at a matrix, there's two operations that are basic if you're doing work with linear algebra, and that is the command np.arrange. Let's put a little question. That's going to create an array for us where we can give the starting value, the stop value, and what the step is. So let's try that. And again, by hitting question mark with you got all these details about that, and you've got some examples down here. Matter of fact, we can just look at the examples they show. NP arrange 3, well, where's the starting value? Where's the step value? Well, if you don't give it, the default starting value is 0, and the step value is 1. However, when you say NP arrange 3, it's going to return 3 values, but it doesn't include the final value. All right. So if I have np.arrange 10, it's going to go from 0 up to 9. Or if I have np.arrange, I can give the starting value. I want 1. Maybe I want 1 to 10. So I'll go 1, 11. And that will give me 1 through 10. Also, there's the len space. np.len space, question mark. Now what this is going to do, similar to NP arrange, but you can, instead of giving you a step value, notice start value, stop value, and you just say how many values you want in between those two. It's the third parameter. And then you can also specify whether you want the endpoint to be included. You have that option. So here the default is the endpoint. The endpoint is set to true. So let's see that behavior here. np.len space 1, 10. Say I want 10 values. Here the endpoint is included. Now, let me go back to our vector A. Here it is. Python uses zero-based indexing. That means the first entry in a vector or array has index value 0. So if I want to access the first entry in here, which is a 1, the way you do that is A bracket. So let's see what gets returned here. A0. 1. Notice that. Okay. Where A1 is not the first value, A1 is the second value, which is a 2 right there. To create a matrix in Numpy, let's do it. Let's go m is equal to np.array. And, well, I could do this. 1, 2, that's my first row in the matrix, comma. Well, I'm going to have one bracket, then give the first row. 1, 2, comma separating the rows. 2, 1. There I have created an array. The first row is 1, 2. Second row is 2, 1. Excuse me. It's a matrix. So let's see how it returns. And we can see what the shape is. It's 2 by 2. Another way you could have done that is you could have said, oh, m is equal to np.array 1, 2, 1, 2. And so that's not a matrix. That's just going to be one-dimensional array. But then you add this little reshape. And say reshape that 2 by 2. And there's our matrix. Now I want to create a 10 by 3 matrix. Create a 10 by 3 matrix of random integers. We make them random integers. We want the integer values to be between, let's say, 1 and 10. So I'll show you how we could do that. We go m is equal to np dot random. Okay, so now that is a submodule of NumPy, random dot. So we'll put another, and taking an operation out of that module called rand integer. The range 1 to 10. Give me some random integers that fall in that range. Size, let's have 10 rows, 3 columns of them. And there it is. So there is a 10 by 3 matrix of random integers. And I want to just take a moment to show you how we can access entries in that matrix. Let's first do an m.shape. Yep, it's 10 by 3. Well, if I want the entry on the first row, first column, you're going to do m, and you have to do these like 2 numbers here. Row 0, remember we start counting from 0, column 0. There it is, it's a 6. Try this again. If I want the entry on row 3, which is the 4th row, column 1. Well, let's look up here and see what it should be. 0, 1, 2, 3. There's row 3, column 1. It should return a 7. Now, if I just hit M with a number, 1, what that's going to do is just return one of the rows. So M1 says, give me row 1, which is 3, 2, 2. Now, here's something to be careful with. It returns, the row 1 in that matrix is a row vector. And we asked for row 1. But it just returned, hey, look at what the shape of this is. M1.shape. It just returns a one-dimensional array. Now, if you want, you could do this. Now that, you can see I have 2 brackets, and that returns a row vector. Suppose I want the column 1 from M. So a colon has special meaning. It means everything. It means everything in the first column. And I want the, what do we say, row number 1. Let's look and see what we get there. Let's go back and look at M to compare that. Yep, 9, 2, 7, 7, 8. 9, 2, 7, 7, 8. So this colon operator, if you just put the colon by itself, it means, see, this is the row. It says, give me everything, okay, all row values, just 1 column value. Well, now if you just want the first 3 row values, you could do this. M, starting from 0 to 3. And remember, it's not going to include that last value. So this is giving me row numbers 0, 1, 2, and which columns do we want? Well, let's take all the columns. So that will actually return the first 3 rows. Now, this is going to be interesting. Notice here, when you pulled out a single row, it gave you a one-dimensional array, but this returns a matrix. So there is 1, 2, 3, your first 3 rows. Well, operating on this, let's do the following. We talk about the norm of a vector, which is like the magnitude, the norm of a vector. And the way we could do that, you might say, oh, well, let me find norm. So you might go, NumPy should do norm. So I'm going to go np.n asterisk to see if I can find a norm. So look all down here. Let's see, no norm. See that? No norm. Well, it turns out that NumPy has a submodule called linear algebra. Submodule linear algebra. And it's going to be, you want to access, you go np.ilinalg to access that. So if I go np.linalg.n question mark norm. So I want to find the norm. Hey, let's go a is equal to something we know what the norm is, so it makes sense, like 3, 4. So we know the norm of that vector, it better return 5. So np I'm not happy. What happened to our x? Right, we lost our, no, it's m, our matrix. Here it is. What if I want to calculate the norm of each row and return that? I want to calculate the norm of each row in this matrix. Let's try this. Oh, that didn't work. What that did, it gave you the norm of a matrix. Yes, a norm of a matrix is defined. We won't discuss that right now. So how we could tell that we want the norm of each row is we could do this. Give me the norm of matrix M, and I could tell it what axis to operate on. Axis equal to 1. That is the rows. And so it should return 10 values, each value representing the norm. And there they are. To confirm that, suppose I asked her, hey, what is the norm of matrix row 0? See if I get that 10 right there back. If you want the norm of the columns, that's going to be axis equal to 0. It returns 3 values. Now, what we could also do is we can find the average value, the mean. The average value of 3 and 4 is 3.5. So what if I do that mean operation to our matrix? Okay, well, it comes back with this 4.9. But if I do m dot mean Let's try this. Axis equal to 0. Oh, so here I got the average value of each of the columns. The average value of each of the columns. And if I redo that and change it to 1, that took that matrix and gave me the average value of each of the rows. Now, if our columns are what we're interested in, the columns, sometimes we like to demean the columns. That's D-E-M-E-A-N. I'm not sure if it's a word, but we use it. Demean. That means I want to normalize all the columns so the mean is 0. And thus, if I take M, matrix M, and I subtract it from M dot mean axis equal to 0. Okay. M is equal to M dot mean. I want to take M and subtract that. Now, so it looks like there's going to be a problem here because you're taking a matrix, it's 10 by 3, and you're subtracting 3, an element with 3, an array with 3 entries. Let's just see what it does. Well, it worked. Okay. What we were trying to do was find the mean of this column and then subtract that mean from each value, which now, if that worked, that means that the mean, we've demeaned the columns, and they all should have a mean value of 0. Let's test that. Now, my last operation, the answer, we can reference that answer with this underscore. See if I hit that underscore? That gives me that last answer. Hey, by the way, I hit a clear right here to clear the screen. So, oh, and I can use this up arrow to recall recall operations. I'm using the up arrow to scroll through. So I want to go back to this. Oh, I just noticed what I did. I changed M, so M now is a new. I did save my result in M, so we got a new matrix M now. Let's look at it. There it is. Let's find the mean of that. M dot mean axis. This is essentially 0. 10 to the minus 16, 10 to the minus 16, 10 to the minus 16. The mean of each column is 0. So how did that work? How was it that we took a 10 by 3 and subtracted a 1 by 3 from it? Well, what it did was it broadcast. So that's a word to look at if you're interested. There was a broadcast operation involved in there. It took that 1 by 3 and broadcasted it down for each of these. Let me give you an example of what I mean. Let's look at, here's B. Here's B. Suppose I take B minus 1. Now, in a linear algebra class, this is not defined. But in Numpy, what it's going to do, it's going to take that 1 and make it a 1, 1, 1, and it's going to subtract 1 from each entry. So if it works, I should get 3, 4, 5. So that's the broadcasting that I'm referring to. Let's try it. All right. So we have something called namespace. And when you do who, the namespace is what your current variables are and your current modules are. Okay, so we've looked at vectors, doing dot product with vectors, calculating norm. You could do this help. np.len.algebra, let's see that. And oh, you get this nice stuff here. Some linear algebra basics. You can do a norm, inverse, solving determinants, least squares, pseudo-inverse, etc. So these are some operations that are available. For the final thing, I want to talk about something that's going to help with the upcoming project called list comprehensions. And it's a way of building list. And you say, no, I need an array. Well, you build a list and you could turn a list into an array by just doing Numpy array. But suppose I have this. Suppose I want to get a list of tuples where I want the first value to be a and a second value to be a squared. Notice how a squared is represented in Python, a star star 2. So to open my list, I've got this bracket, and it's going to be a list of tuples. And then we say for a in, we could put a list here. We want what a values you want. Maybe I want 1, 2, 3, and let me jump up to 5. Close that. Close your list. And what this is going to do is a list comprehension. It's going to return a list. In this case, a list of tuples. A took on the values 1, 2, 3, 5. So our first value here is 1, 2, 3, 5. A squared. Each of those squared. That worked. And what I'd like to do is to show how we can use Numpy to plot a unit circle. Now you might recall from calculus that a unit circle could be expressed parametrically like this. Cosine t, comma, sine t. So if you think of these as, x is cosine t, y is sine t, where t is going to go from 0 to 2 pi. That defines the radius is 1. That will define a unit circle. So let's use list comprehension to get a bunch of points on that unit circle. The first thing I want to need is, notice this. If I type in cosine of 1.2, here, cosine's not defined. So it's not part of the standard library, if you will. And also if I hit pi, that doesn't work. So what we could do is we could do numpy.pi, and you go np.sine of 12. Okay, so NumPy has this. But it gets a little tedious always having to type in np.sine. So I'm going to do this. Notice this. I'm going to take import from, I'm not sure if I got this right, from NumPy. Let's try this, see if this works. Import from NumPy. Sine. Suddenly I'm losing. From NumPy, import sine, cosine, pi. Oh, that works now. So you don't have to put that NP there anymore. Okay, so here we go. I'm going to create a list of points around the unit circle. List comprehension. Cosine t, sine t, so I'm going to create a list of points, and this is for t in, let's try this, linspace, go from 0 to 2 pi, and now however many points you want. Let's choose 100 points. And what we need to do is let's call this data. Okay. Linspace. Okay, so we misspelled linspace. Let's look at that data. There it is. 100 points evenly spaced around the circle. And what I like to do is plot those points. Well, to plot them, we need to import a plotting tool called matplot library. So we are going to say import and we're going to import it as plot. So when we refer to it, we just have to put plot. Try this again. matplotlib.pyplot. Import matplotlib. Third try should be the charm. Lib for library. Import matplotlib.pyplot as plot. Oh, got it. And to plot those points, well, before we plot those points, let me just kind of show you how matplotlib works. Let me do one quick thing here. Let's create an array t is equal to np dot hey, let's do this plot interactive on. Execute that. Let's create some, I want to plot a sine wave. So I want to create some values. T, I want it to be NP. Go again from 0 to pi. Let's just get 15 points. And then let's plot it. We're going to say plot.plot. Now, if you want to know how it works, again, you can put that question mark there and learn all about how it works. So we say plot.plot and just give it the x values, which is t, sine t. And let's do this if it works. Okay. It didn't like that. Okay, I just did 15 points because I wanted you to see the points. And I also did this dot dash. Okay, so give us that. Close that. Now, if you just want to plot an individual point, like, hey, let me put a plot on top of this. Suppose I want to plot just a point. Let's plot the point 1, 1. Plot the point 1, 1, 1, 1. And let's put a O there when we plot it. And let's look back here. There's the point 1, 1. So now I want to plot my data. So remove that. Let's look at that data one more time. We have to somehow let matplotlib know this is a list of points. I won't go into the details now about how this works, but to do this, it's going to require this. We're going to have to do this star zip star data. That's just to take this to put that data in a format so it looks like a set of points to matplotlib. And then let's say, okay, I think we got everything right. And let's just, inside these single quotes is what you want to plot. So let's just do a point. And let's see if that works. There we go. Okay. Well, I think it was just 100 points. We chose more to have been a circle. Let's say plot dot axis. So it will look like a circle. And there we go. There's our circle. So again, we used a list comprehension to generate these points. And they're stored. Now, if we look at data, let me try to do this. We have this interactive on. We could do things like add a grid to the plot. Add a title. And now for our last, we're still working with this. This is the last thing. I want to apply a transformation to this. So if I define a matrix A as being equal to so here's our matrix A. 2 by 2. Now, if you want to multiply that matrix by a vector, the vector has to be the right size. Okay, it's going to have to be a 2 by 1 vector. So let's see, let's get A. What size is A? A is just a one-dimensional array. Hey, but it will work. If we take A and we do matrix multiplication, the ampersand times A, that will work. 1, 2. Okay, 1, 2, 3, 4. That's going to be 3 plus 8, 11, 11. Yep, that's correct. And in fact, my matrix 1, 2, that's not what I wanted. 1, 2, 1, 2. Let me change A. I want it to be 1, 2, 2, 1. I want the second row to be 2, 1. That's better. But if I take A and reshape it to a row vector, and if we take the matrix A and try to multiply it by the vector little a, we should get an error because those sizes do not fit. They're not aligned. But if we turn A into a column vector, A, the vector A, by transposing it, and we get what we should get. Now notice this. A is 3, 4. You multiply it by a matrix, and it transforms this vector into another vector. It changes its magnitude and its direction. What I'd like to do is take this matrix here and apply it to every one of these dots. Okay, so I'd like to apply it to every one of those dots and see what the result is. Now, this is a unit circle, So all of these have a magnitude, all these points have a magnitude of 1. So I'm just kind of want to see what the behavior of this transformation is. So I'm going to apply it to this. Let's see, how can we do that? Got to finish up here. A, my data, the shape of the data is, oh, right now the data is a list, so I'm going to change it to an array. So I'm going to take data is equal to np.array. See, notice what happened. I tried to determine the shape of data. But remember, we created that using a list comprehension, and therefore it's a list. That's why it returned an error when we tried to see what the shape was. Hey, this is a list. It has no attribute shape. Let's change it to a Numpy array, doing that command. Okay. Now data.shape. It's 100 by 2. Well, what we could do is turn that into, we're not going to be able to multiply. What we want to do is take A and multiply it by each of these rows, because each of these rows represent a point. So what I could do is I could take the data and do the transpose on it. Data equal to data.transpose. And we look at data.shape now, can't see from what you see there, it's 2 rows by 100 columns. So each column is a different point. And I could take my transformation matrix A and multiply it by this, and it will transform every column. So I'm going to take, let's call it values, is equal to A, and we'll go give more detail of this in class, times data. All right. So here are the new values. And we want to plot those on top of this to see what happens. Well, the values are 2 by 100. Let me transpose that back, because we want to see how we can plot all those points. And now let's try it. I'm going to plot all my results. And oh, perfect. Hey, this is a very fundamental result. A circle times a matrix is an ellipse. And what it tells us is that now the result, now this vector here, these points are vectors. This vector here is not necessarily the image of this vector right here. Okay, because see, there could be some rotation that's going on. But some vector gets stretched more than any other vector. Okay? So if I try to maximize the product of A times X, there's some vector that gets maximum stretch. Okay? And how much that stretch is. So this is something that will be studied. I think that's quite enough for a quick introduction to using Python with linear algebra. Thanks for listening in. We're going to sign off.